Okay, so calculate the total mechanical energy of the object. The idea here is that total mechanical energy is the result of potential energy plus kinetic energy. So it's easy to figure out the potential energy. You can do that from the function. It's the kinetic energy that can be an issue. The key here, though, is that it tells us that at x equals -5, the velocity is 2 meters per second. So we can easily figure out the kinetic energy there. Kinetic energy equals 1/2 mv squared. So 1/2 the mass of the object is 3 kilograms. The speed at that location is 2 squared. So 1/2, so that's 4 times 3 and half of that. So that's 6 joules. The object's kinetic energy is 6 joules at x equals -0.5. Well, what's its potential energy at x equals -0.5? We will use the equation. So 4.0 times -0.5 squared, that ends up being exactly 1 joule. So now the potential energy is 1, the kinetic energy is 6, the total energy is 7 joules, and that's the answer to A. B, calculate the x-coordinate of any points at which the object has 0 kinetic energy. The key here is that an object will have 0 kinetic energy when all of its energy is in the form of potential energy. You can see that it still equals 7 joules over here. It always has to equal 7 joules. So what I'm going to do is I'm going to take the potential energy function, U equals 4x squared, and I'm going to set the potential energy equal to 7. 7 equals 4x squared, and so that means that square root of 7/4 is what the x-coordinate would be equal to, and that is approximately 1.32 meters. That's the answer to B. C, calculate the magnitude of the momentum. Oh, you know what? That one, you guys don't know how to do yet. Sorry about that. D, calculate the magnitude of the acceleration of the object as it passes x equals 0.6. So what does acceleration have to do with potential energy and kinetic energy? Well, what we have learned is that force, and force is closely related to acceleration, is equal to -du dx. So if I can calculate the force, I can use net force equals ma to get the acceleration. So I'm going to take the derivative of our potential energy function, -d 4x squared dx. And so 2 times 4 is 8, and then drop it to x, put a negative sign in front of it. So -8x is a formula for the force, and we are talking about at the location 0.6. So 8 times 0.6 is equal to, I believe, 4.8 newtons. This would be -4.8 newtons. And then using net force equals ma, so -4.8 newtons equals 3 kilograms. You can get the acceleration here. 4.8 divided by 3 is equal to -1.6. They did, however, ask for the magnitude, so we only need to write down 1.6. Okay, we erase that, get to the last part, which involves graphs. Okay, here we are. Sketch graphs the object's position versus time and kinetic energy versus time. So how are we going to do the position versus time? Well, the thought that came to my mind is, first of all, let's think about what the potential energy graph would look like. U equals 4x squared. So I'm drawing an axis here. Here's the potential energy. Here's 0. Well, what does a graph of 4x squared look like? That's not a difficult graph to imagine. It looks like that. It's a parabola. And in fact, if you get into the negative x region, it looks exactly the same, a mirror image, because when you square a negative number, it just becomes a positive value. So that's what the object's potential energy graph looks like. So when the object has a certain amount of energy, let's say this is the total energy. Let's say this represents 7 joules. You can think about how the object will behave. I've mentioned before that you can think of a potential energy graph as a surface and put a marble here on the surface and let it go from rest here, because that's where its total energy is. What would it do? Well, it would roll down, get to the bottom, it would roll back up, and then it would repeat that process. It would just keep doing this over and over and over and over, back and forth, back and forth. This is actually the potential energy graph of a spring. So picture a spring going back and forth and back and forth. And so the way I would graph that, they said start at x equals 0 at time t0, so that means we're right here. Now we could start by going to the right or start by going to the left. Let's assume, and either way would be correct. I'm going to go to the right. And so what's going to happen is you're going to slow down, slow down, slow down, slow down, slow down, stop. And then you're going to speed up, speed up, speed up, back towards 0. You're going to blow past 0, slow down, slow down, slow down in the negative region, and then back to 0. Lo and behold, we have a sine graph. So let me just maybe do one more cycle of that. So then what is the kinetic energy going to look like? And how is kinetic energy related to the graph that we just did, which is x? Well, kinetic energy equals 1/2 mv squared. So that means kinetic energy is related to speed squared. And it comes to mind, one way of thinking about this is that speed is the derivative, or in other words, the slope of a position versus time graph. So not the only way to do this, but I'm going to think about the slope of this graph. And you know, I want to just mark some important locations here to help me synchronize these two graphs with one another. That's probably enough. So let's think about the slope right here. What kind of a slope are we looking at? A very steep positive slope, a high positive value. So the kinetic energy starts out high and positive. And what are we approaching? What's the slope here? The slope here is 0. And what about there? Well, the slope is very, very steep, but it's a negative slope. However, remember, speed gets squared in the kinetic energy equation. So even though this is a negative slope, the velocity is going to get squared, and so we're going to end up with a positive value at the same height as this one over here. This slope is positive, this slope is negative, but when you square them, you end up with the same number. And then this cycle is just going to repeat. 0, same spot here, 0, same spot here, and then I'm just going to connect them smoothly with a sinusoidal function. That's a word.